Yeah, I do.
Awesome. Well, I guess we can start.
Okay, let me hide the controls. Okay. So yeah, I wonder, let me consult with everybody how we should do this. Should, like, one option is for me to give like a 15-20 minute presentation to what Cqlin is, but I'm not sure of the format, even though I've been here once. Like, another option is just have Q&A if people read the paper and want to ask something. Any opinions?
Yeah, I wasn't able to go through it all, so I think doing an intro, at least from my side, would be preferable.
Okay, yeah, that totally makes sense. All right, so yeah, please feel free to interrupt at any point. So I'm going to use these slides I used at ZK Summit, but I'm going to use them in a different order. So if someone saw the ZK Summit, hopefully there'll be like something unexpected. Was that, just curious, did anybody see the ZK Summit 9 presentation I gave?
Yeah, I've seen it.
Oh, cool.
But
cool.
I think it's good actually to start here, because I guess it was kind of tight on time at the end, just when it was getting pretty interesting.
Oh, okay. I'm glad to hear it was getting interesting. Okay. Or I guess that can be a polite way to say when it got complicated.
That also.
And understand. Anyway, right. So let me, at ZK Summit, you can find it online. I sort of start with this like general exposition to where we are in pairing based protocols. And here, let me dive straight away to what is the specific problem the Cqlin paper addresses. So look at this setting. You have some fixed n times n matrix. It's fixed in advance. Yeah, and the prover has some polynomial of degree less than n. The verifier has a commitment to this polynomial. And we look at the vector of size n, which is just f's values on a subgroup of size n. And now the prover wants to show that m times a is 0, and the cool thing, the interesting thing is we want to do it in O of n operations. So right, the matrix here is arbitrary, so it can have n squared non-zero entries. But still, we want to be able to do it after pre-processing in O of n time. Yeah, and that's and this is what the Cqlin paper does. it turned out that there was actually an implicit, you could argue implicit, very implicit protocol that gives the same asymptotics in a paper a few years ago, GKMMM, the first paper on universal and updatable snarks. Not very well known. The reason it's not, I'm going here a little on a tangent. The reason that that paper got Kohlweiss, Mahler, two more M's, Myers and Michael John. The reason it wasn't, this paper wasn't too well known was that it had a quadratic setup, but, or actually worse than quadratic, but quadratic here meaning n squared. So for us, n squared, we are also going to have an n squared setup, but for us, like, that's just the size of the input. Like the matrix could be a full matrix, whereas in that context of that paper, the matrix was like O of n sparse because it came from some circuit that was transformed into an R1CS instance. All right, so that was a bit of a tangent on related work, but let me ask, before we continue, if the problem we're trying to solve is clear. But okay, commitment means KZG commitment, just to be totally clear. So let me ask if stop to ask if there's any questions about what the result is or any other questions.
Does it need to be KCG commitment, or are there any weaker, homomorphic, any weaker requirements?
Yeah, that's a great question. So for now, it totally needs to be a KZG commitment because we're going to use the multiplicative properties of the pairing. Okay. Sorry. So let me show you a little about how Cqlin works. So it's part of a general methodology that we call cached quotients. So let me go back on in my slides to show you what cached quotients are. So let's talk a second about sparse. I gotta talk for 1 second about how I hate Zoom. What is all this hovering flying stuff where I either have to choose to like not see the people and myself, or I have to like constantly move this stuff around. Like I don't get it. Why don't they do just the Google thing that
Yeah, it's a pain in the ass. They should have like the things on the side and then squeeze the thing in the middle.
Well, okay. I just I thought I'd try to get through the talk without saying anything bad about Zoom, but I couldn't make it. Okay, so let's talk for a second about sparse polynomials. So what do I mean by sparse polynomials? Let's think we have two parameters, little n and big N, and little n is much smaller, and we have some fixed set of big N polynomials, B1 to B capital N. So what does it mean for a polynomial to be sparse in the basis B? Well, naturally, it just means that, so A is little n sparse in the base B if we can write A as a combination of the B's where only little n of the b's will have non-zero coefficient. So that's what we mean by sparse polynomials. You know, right, usually B is just the Lagrange base of a subgroup, in which case the sparsity, it exactly corresponds to how many non-zero values A has on the subgroup. But we're going to see that, you know, B can be other things except a Lagrange base. Why do we like sparse polynomials? Because we can do this this nice thing of pre-compute. If we expect to work with polynomials that are sparse in some bases, we can pre-compute the commitments of the bases. And then when we, during a protocol or proving time, when we get a little n sparse polynomial, we can compute its commitment in only little n operations.
It looks like a very typical trade-off between the storage cost and the time consumption. It's like, yeah, but if the big N is very large, then the cost would be very high. And yeah, I briefly read the paper. So is that one of the goal of this paper? Try to reduce complexity with big N here.
I mean, yeah, I mean, that's a good point in general. It actually does happen to be that in this paper, the big N is, I mean, is actually not going to be too large, but in our previous paper, CQ, then yeah, that's a big issue. There's a, yeah, you need to store a big pre-processed string, or you know, query it, you know, from some provider. Yeah.
Okay. Yeah. Also, the Cqlin paper was recommended yesterday by another people to me. So yeah.
Oh, cool. Well, thanks to them for recommending our papers.
Very popular paper.
Oh, okay, glad to hear. So, okay, so that's sparse polynomials. And now let's talk about what do we exactly call the cache quotients method. So I'm going to describe some setting, which might seem a little abstract, a little general, but you know, and very soon we'll jump into the how to use it for this lin check problem we want to solve. So the setting of cache quotients is that you have two polynomials, t and z, and think of the degree of z as capital N, and typically the degree of t is also something of that size. And the prover has some little n sparse polynomial a, and in some basis, think of maybe just a Lagrange basis, and the prover has some r of degree smaller than capital N. The verifier has the commitments to these polynomials a and r. And now what does the prover want to show? The prover wants to show that a times t is equal to r mod z. Okay, so let's, right, so a is the little n sparse polynomial of the prover. T is one of the pre-processed polynomials. Z is also pre-processed. R is a prover polynomial. And the prover wants to show that a times t is equal to r mod z. And they want to do it in little o of n operations. So any questions about this this setting?
When I was reading your paper, actually, I have a question about the Z, the choice of Z here, but I think we can go to the details later about this part.
Okay. Right. So how do we do something like this? So we want to show that A times T is equal to R mod Z. And as we all know, this is where quotients come in. This is exactly equivalent to the existence of some Q, such that A times T is equal to Z times Q plus R. And right in Q, right, Q is going to have a pretty large degree potentially. It's going to have a degree something also like capital N potentially. Right. Think of it. Think of everybody having degrees roughly capital N, A, T, Z, R. So we don't have time to compute actually compute Q. But the point is, we can still compute the commitment to Q. And why is this? Well, because we can do this thing. For every I, we're going to pre-compute the commitment to Qi. Where what is Qi? So right, we have our basis of the B's that A is sparse in. So for every Bi, we can pre-compute the commitment to the corresponding Q, the Qi that comes up when you multiply Bi by T and divide by Z. So Qi is, remember, B's are the basis, and that A is sparse in, and Qi is the quotient you get when multiplying Bi by T and dividing by Z. So it's the Qi that satisfies this equation for some Ri of degree smaller than capital N. And we're going to, in a pre-processing step, we're going to compute the commitments of Qi for each I. And this is where the name comes from, the commitments to the Qi's. This is what we call the cached quotients. So is it clear what we're computing here in this pre-processing? Any questions about that?
Shouldn't there be a coefficient, like say small AI in front of the BI?
So I mean, so A is gonna, when you write A in the basis of the BIs, you have, it's gonna be some small AI BI. But you don't need that small AI here. You don't know it also, because A, you'll only get it later.
So this is where you need the linearity, right? With that A and the B.
Yeah. So that's what we'll see. We'll see next. So yeah, and we're also going to compute the commitment of Z and T in pre-processing, of course. And yeah, and now the idea is that, why does this help us? Because Q inherits A's sparseness. So right, again, A is this sum AI BI, where only N AIs are non-zero. And what you can check, just because of the linearity of division, right? That A plus B, or let's use different letters, that C plus D divided by E is equal to C divided by E plus D divided by E. So just by the linearity of division, Q's representation in the Qi's is going to be the same as A's in the Bi's. So in particular, Q is going to be sparse and little n sparse in this base of the Qi's. And because of this, we can compute after we have our cached quotients, we can compute the commitment to Q in little n operations. And okay, now the question is, okay, the verifier has the commitment to Q. Does that help us when we have just the commitment to Q and not Q itself? And here comes another, right, the power of pairings. Since we're in KZG and a pairing friendly curve, so we want to check this equation, is AT equal to QZ plus R? And we just have the commitments to the polynomials. We don't have the polynomials themselves, right? Even the prover doesn't actually know Q. He doesn't have time to compute it. But still, we can check this equation directly from the verifier. Can check this equation directly from the commitments to these polynomials using pairings. Yeah, so any questions on this before we get into the how we apply this in the Cqlin protocol?
I don't know if my understanding is correct. Do you mean that even though we don't calculate the Q, but since we have the commitment of the Q, then we can check the equation with pairing. Is that what you want to say?
Yeah, exactly, right. You'll check that the pairing of the commitment of A with the commitment of T is equal to the pairing of the commitment of Q with the commitment of Z times the pairing of the commitment of R with like 1 encoded in the group.
Okay. Yeah, thank you.
And so right, a little point here is when I say commitment, so for T and Z, I mean like the commitment in G2. So when we say KZG commitment, we always mean in G1, but yeah, for T and Z, you'll compute sort of the commitment in G2, so you can pair it. Yeah, so that's the cache quotients method in generality. And now let's see how we can use it to solve this this lin check problem. So right, so again, let me remind you, we have a commitment, we have a predetermined matrix M, we have a commitment to F, A is F's values in a subgroup H, and we want to prove that M times A is the 0 vector. So let's call L1 to Ln, L small n, let that be a Lagrange basis of H. So right, this subgroup of size little n. So what we wanted to show now is that we can reduce this problem to the setting in the cache quotients method. So So first thing is we're going to represent the matrix M by a polynomial of degree roughly n squared. So that we'll also just call M. So the polynomial M is some Mij, where the Mij element, the ij element, I'm multiplying it by Li of x to the n times Lj of x. So I'm sort of using like x to the n as a second independent variable. So you can, if it helps, you can sort of think of it as Mij of Liy times Ljx. But it's nice to be able to work with a univariate SRS. Okay, so this is a polynomial representing the matrix, and and now we're going to take z to be x to the n squared minus 1, like a vanishing polynomial of a subgroup of size n squared. And also we're going to sort of represent our vector by the polynomial a of x, which is equal to f of x to the n. So the sort of the vector we want to multiply the matrix by is f's values on h, but it'll be convenient to actually have the polynomial f of x to the n. So in the Cqlin protocol, we're going to do some random, like the prover is going to send this a, and we're going to do some random consistency check that a is really equal to f of x to the n. And now let's look at, after we've defined all these polynomials, let's look at a times m mod z. And if you have a pen and paper in 10 minutes, you can check that r is equal to this thing. So it's a little complicated. So the thing maybe to notice about r is if you look at the internal, okay, I realize now that there's something I did. I defined things, so I'm actually, I talked about m times a, but I think what I'm doing is more like a times m. So sorry for that, but right, if you look at okay, what I want to say is if you look at, for a given j, if you look at the internal sum, right, so we have sum ai over i, ai times mij times li of x to the n. So if you ignore the li of x to the n, then what do we have? We have the inner product of the vector a with the ith column of the matrix. So sort of if we didn't have the li of x to the n, then we would exactly have that, like the coefficient of Lj is 0 if and only if like the inner product with the jth column of the matrix is 0, which is sort of what we want to check for every j. So sort of R gives us what we want, but with this factor Li x to the n that we need to get rid of. But actually, before saying anything else, let me give you a few minutes to ask questions and just stare at this.
Yes, sorry. So is that second summand? It's like an it's an inner sum on the outer one here, right?
An inner sum on what?
Sorry, yeah. So the AI times Mij. This sum is an inner one of the sum of LJs. See what I mean?
Yes.
Yeah. Okay.
Here is my question. I want to ask before. The choice of Z here. I don't understand why, and is that could be anything else or yeah.
The choice of Z. The object of the Liam, feel also free to chime in. But yeah, the object of the choice of Z is to like yeah, you can take this.
I in principle you can use any Z. Using the roots of unity vanishing polynomial gives you a good setup complexity. If you were to use just like some Z with a bunch of distinct roots, that would also work. The Lagrange polynomials would exist and everything would work out, but the setup time would be like n squared log squared n instead of n squared log n.
Okay.
That's what you're asking.
Yeah. Actually, what I'm thinking about now is like, if I use the field, a binary field, or a field extended by the binary, I mean this Z actually can be used to construct the Galois field. So I don't know if it's possible or to construct Galois field GF2 or GF2 power 2 something else for it. I didn't notice that before, but it looks if this one holds, it shouldn't be a problem to construct a Galois field.
I'm not sure if I completely follow. Here we assume Z completely splits over the fields that we're working over. How do you mean? How would you use that?
Yeah, because I mean Galois fields is kind of tricky because it's like it's near to be if it's a binary based Galois field, it's near to be user field. F is binary, and also it need to construct based on the polynomial. It's need to be extended by the polynomial. So I mean it works a little bit different with typical KZG commitment here. So that's why I'm asking this question. But yeah, anyway, yeah, we can continue. We can discuss that later.
Okay.
Yeah, I think it's maybe a tricky problem.
Okay.
Thank you, Guy.
So I think maybe it will be useful to wait. Am I still muted or God? I hate Zoom.
No, you're not.
So yeah, I think it'll be helpful to see the one nice thing about this Z. If we go to the paper, where's this thing? Where is this lemma? Yeah, basically, when you multiply LIs with x to the n inside, this is the nice thing about this Z, that Li squared becomes Li, and Li times Lj goes to 0.
I just realized another thing about this Z is that we can use the evaluate at 0 sum check. If you don't use this Z, then that does not work in general. And so in fact, it may not work with arbitrary Z unless you substitute a different sum check.
Yeah, yeah. Yeah, that's true. That's true. Thank you.
Yeah, so right, so we were at this this point that R is sort of what we want, except this Li of x to the n, right? But if we can erase it, we'll exactly have the inner products with the columns that we want to check. So to get rid of this Li of x to the n, right, but the idea is that now if we mod out, given this R, if we mod out by x to the n, then it's exactly going to get rid of this factor Li of x to the n, or it's going to give us some scalar like 1 over n, but m, so we can conclude that m times a is equal to 0 if and only if R is equal to 0 mod x to the n.
Yeah, this is the place I totally lost when I was reading the paper.
Well, now are you less lost or also?
Yeah, I still have some question. Why here? Why here is modular x power to the n here? Because previously you use z is x power to the n square minus 1. So I didn't get why this still holds.
Why this last thing at the bottom holds?
Yeah, the bottom.
So let's assume that R is this is R. So now if I mod out this R by x to the n, it's like replacing inside the Li, replacing the x to the n by 0. And Li of 0 is equal to 1 over n for every I. And at the same time, modding up by x to the n, it won't do anything to this Ljx because its degree is smaller than n.
Do you mean that because here all the LI is the LRX power to the n. So if you module the x power to the n, then it will make Rx equal to 0. Did I miss something?
Can you say that again?
No, because here, I mean, why the button holds? I don't know if my understanding is correct. But why the button line holds? Just because here the input of Li is x power to the n. So if you module x power to the n, then actually it makes input of Li be 0. And
Right.
then everything else could make everything else 0, something like that.
No. So it'll make the Li of x to the n. So Li of 0 is equal to the constant 1 over n for every I.
Yeah.
So if you mod out by x to the n, it's like losing this factor of Li, x to the n, and putting a 1 over n, multiplying the whole thing.
Mm-hmm. Yeah, if that's true, why Rx should equal to 0? If here is 1 over the n, and then you sum all you add all these things together.
Right, because so if m times a, so it should be a times m. If a times m is 0.
Ah,
then
okay.
means that,
Okay.
yeah.
Okay. That's okay. That's a reason. Oh yeah. I got your point. I think it's too. I think too much. Just think too much.
Yeah. I think this requires like I should write a few more lines. Yeah.
Much clear. Thank you very much.
So now the question is, if these checks we want to do, they fit into the cache quotients method, right? So again, where there's two checks we want to do. We want to first check that R is A times M mod Z, and then we want to check that I guess R that R is 0 mod x to the n. So let's think of the first check. R is equal to A times M mod Z. Does that fit into the cache quotients setting? So it does. Why? Because M and Z are predefined, and A is little and sparse, right? Why is A little and, okay, let me go to the next slide. So A is little and sparse in this basis, Li of x to the n. I mean, it's funny to call it sparse because like these are all the elements of the basis, but right, A, although it has degree like roughly n squared, we can write it in using these little n basis elements. Just because it's a polynomial that's an nth power, so a little nth power, so you can write it in this basis. So again, so we have what we have fits into the cache quotient setting, because we're multiplying a is little, a is sparse. We're multiplying by m and dividing by z, where m and z are predetermined. So that's why we can show that so we can show, right, so that's why we can use the method to show that in little n prover operations to show that the first thing is true. And now for the second thing, so again, R is not a polynomial we want to work with directly. It has degree roughly capital N. But the point is R is also sparse in a basis that we know in advance. So what is this basis exactly? It's the basis. I'll have to go back. So when we pre-compute the QIs we need, then R is going to end up being sparse in this basis of the RIs. It's just this thing that if Q is some AI QI, then the same thing works for the remainder. So R is going to be some AI RI. So let me go back here. So yeah, so again, so this is the idea that we can use the cache quotients method to show both these modular equalities and only in little n prover operations. Yeah, so maybe I'll now just give some time for Q&A because I'm sure I've lost. I don't know if anybody made it till the end.
Okay, so with the second check here, what we basically ensure is that R of X doesn't have any terms which have degree, X of like nth degree or higher. How do we prove by that it doesn't have any? Okay, I think I see. So if this holds true, it means that there are no terms smaller than degree n, right?
Yeah, it does mean that. Yeah.
Okay, yeah, this makes sense.
Yeah, that's another way to look at it. It means if you're 0 mod x to the n, then there's no terms degree smaller than n. And that means that this inner sum like has to always be wait, is that actually how well, never mind. Actually, I don't see it till the end, but if it clarifies it for you, or what? Maybe repeat what you said, or
Yeah. So we map all the terms which have degree higher than n to 0. That's quotienting out. So we don't really know, just based on this thing mod x to the nth is equal to 0. We don't really know what those higher degree terms are. It could be that one of the terms is like 500 times x to the n plus 1.
Well, wait a sec. When you mod out by x to the n, you're not zeroing all powers of degree. I think you're only zeroing out powers that are like multiples of n.
Like 1n, 2n, 3n, and so on.
Yeah.
Okay, so you map like n plus 1 to 1.
Yeah.
Yeah, right.
Yeah.
Okay, yeah. No, then this should, then it should make sense, but maybe by some probabilistic argument, because you could have like collisions. Like you could have the first coefficient, the coefficient in front of like x could be 5, and then x to the n plus 1 could be -5, and then those cancel each other out.
Yeah, that's what has to happen.
Okay. Thanks.
Doesn't the mod x to the n map the all higher powers of x to 0?
This is what I
Oh,
thought too.
wait a second.
Because it's like 0 times x to something else, right?
Yeah, it
That's-
does.
Oh, you're right. You're right. I got confused with modding out by x to the n minus 1. Maybe. Yeah,
Right.
yeah, right. You're right the first time. Yeah.
Okay. Okay. Yeah, cool.
So you were saying one of the applications would be ZKML, right? Or sort of any situation where we have like a dense matrix.
Yeah, so this should be good in any situation where you have a dense matrix. And in particular, I at least think that so I'm not an expert on this, but I understood that in the ZKML, when you want to show that your prediction is according to a model, you have this computation of like a neural network where it's this alternating a lot of linear operations and then a non-linear operation and then a lot of linear operation. So this linear operation, you can write it as a matrix, and I think it's an arbitrary matrix. It's not a sparse matrix like R1CS.
But where's the trade-off with like the pre-computation time?
Well, I mean, here the trade-off is so if you use this, you have like n squared pre-computation and then n time during the proving, and if you don't do this, then you have n squared during, like if you just use Planck or Marlin for this matrix, you'll have n squared proving time if it's a fully dense matrix.
Mhm. Small n squared, yeah.
Yeah, small n.
Yeah, okay, thanks. Great, so do we have any other questions? I'm aware we've gone a bit over time, but so thanks for extending time a little, Ariel.
Sure.
Thank you
Okay.
guys.
Yeah, if we don't have any other questions, I'd like
Thank
to
you.
thank you both for joining us. So thanks, Ariel. Thanks as well, Liam.
Thanks, everybody.
Thank you.
Much.